Okay. Octavio, can you hear me?
Yes.
I see some reverberation. Okay.
I think the echo was my fault.
Okay. Good. Let's start. So, okay, are you everybody here today? Somebody needs to arrive yet? I don't know. Okay, let's start. So, last lecture, Octavio started to introduce the concept of interaction control of a manipulator whenever it enters in contact with the environment. For now, let's just put this on hold and finish the topic about the task-based control, which means, sorry, I closed the door. So in the previous topic, Octavio started to teach you about how to implement a controller at the end effector. In the end effector space, we saw what to do in terms of a Cartesian control. So whenever we are interested to control only the position of the end effector. Now we want to do something more. We want to also introduce what to do whenever we want to control the orientation of the end effector. And controlling the orientation is not as easy as controlling the position. And we'll see soon why. So control the orientation, as you remember, means controlling the orientation of a frame that is, for example, attached to the end effector or to any other point of the robot. And to do, yeah. 1 second, that's really strange. Before you could see that, right? No, never. Okay. Octavio, can you see everything? The slides?
Yes.
Good. So to control the orientation, we need one thing. We need in essence to make use of the angular part of the Jacobian. You remember the geometric Jacobian that Octavio taught you in the lecture about differential kinematics. So in particular, to implement for example, a PD, proportional derivative controller for the orientation, we need to have a measure of the orientation and also a way to measure the velocity, the change of the orientation, so the angular velocity of the frame. And also a way to map the control law, whenever we computed this control law for the orientation, into torques. And for doing that, we use the angular part of the geometric Jacobian. We can see that we can get, for example, a measure of the angular velocity by multiplying this angular part of the Jacobian times the q dot, the joint velocities, and this way we get a vector, a 3D vector that represents the angular velocity of the end effector frame. And similarly, using you remember the kinetostatic duality, using the transpose of this Jacobian, we can get a mapping between what? between Cartesian moments, so moments at the end effector, into torques. So the same we did for forces, we can do for moments at the angular, at the orientation level. So pay attention that now we talk about no longer about virtual linear forces, but about virtual moments. So these are moment about the axis of the end effector of whom we want to control the orientation. Now, how does the PDE orientation control law looks like? It's just very similar to the Cartesian one. We have the Jacobian transpose, the orientation part of the Jacobian, and we do the transpose. Then we have a term that represents the torsional stiffness, and one is the torsional damping, and the torsional damping multiplies the error for at the velocity level, which is in this case the angular velocity, and this error is it's already in the Euclidean space because we know the angular velocity was defined in the Euclidean space. We don't have any problem. While the torsional stiffness KO, sorry, is O stands for orientation. It's multiplied by the orientation error, and we will see that this is tricky to be computed. It's not that straightforward. I need to, because depends on the representation of orientation that we choose to represent orientation, and we explain in the lecture on angle axis, Euler angles, all different types of representation of orientation that are possible, and we will see a way to compute the orientation error in all that cases. Now, what are these KO and DO equivalent? These are equivalent. For example, the KO matrix is equivalent to if it is diagonal to 3 torsional springs in the 3 directions. So think about the Z direction and think about a torsional spring is like the ones that you have inside a clock in the old clocks at the beginning of the 19th century that you need to charge. So this spring is a torsional spring, and if you multiply this stiffness around the component of this diagonal KO matrix along the Z direction times the component of the error, at in the Z direction, then you can have then you can have a moment around that axis that tries to control the orientation along that about that axis. And the same if you extend the thing to the 3D case, you can get using the 3D vector representing the orientation error, multiplying by the KO matrix, that is this 3 times 3 matrix, you can get out the moment, the restoring moment to achieve the, for example, to take the orientation error down to 0 in this case. This is what we want to do. So this error variable indicates what? Indicates the deviation between the actual and the desired orientation. So, okay, whenever we have the desired frame and the actual frame that are not coincident, we have some orientation error. Okay. Now, so if you compare to the linear case where we define the position error simply subtracting the actual position from the desired one, in the orientation, case orientation, as I said, there are some difficulties that arise due to the fact that we need to consider the algebra, the special algebra of a rotation group. And we cannot just subtract rotation matrix one from each other because we have all the orthonormal constraints to be satisfied. And the expression of the orientation error depends on the particular representation that I remember that we choose for the orientation that I remember to you are the rotation matrix, the angle axis, the Euler angles, and the quaternions. Okay, now to define the rotation error, let's start from the rotation matrix. We consider the rotation matrix representing what represented the desired orientation. So WRD, and also the rotation matrix that represent the actual orientation, which is WRE, where E stands for end effector in this case, but could be whatever frame you want to control. And if we want to visualize, this is the inertial frame, and these are the D frame and the actual frame, and this is the actual orientation and desired orientation. So to get the relative orientation between the effector frame and the desired frame, we apply whatever we learn is the composition of rotation matrix. First, we know that through the homogeneous transforms from the joint angular position, we can get through direct kinematics the rotation matrix representing the orientation of the end effector. Then we can compute, compose in subsequent rotation the relative orientation. This is done the following way. So first we express the desired orientation as from word to desired frame as a composition of the rotation matrix between word and effector, and then from the end effector to the desired frame, which is the thing we are interested to. So to isolate this one, we in essence left multiply by the other term here, how transpose, because if you left multiply by transpose, this term will disappear, and we end up with this expression where we have the right hand side now on the left hand, and we have the relative rotation, the orientation of frame D with respect to frame E, expressed in this way. Now, note that we can define, actually, I had a hard time to, to put together these slides, because in the literature you can find two different ways of defining the orientation error, depending on the fact if you are considering as a reference the end effector frame or the desired frame. And in Siciliano book, unfortunately, they use the other expression, which I don't like, because we want to define an error like from the end effector we want to go into the desired frame and not the other way around. But there's nothing wrong in that. They just some sign change, and we will see some expression in the formula with the quaternions will be different. But whatever I choose to be my convention, which is using the frame A as reference, will be consistent with all the formula we use in this lecture. Just pay attention that if you look in the books and you find the other formula, which is in essence, I think this one, is because you get the orientation error in the other way. So the drawback of using rotation matrix directly is that we have difficulty in handling the 9 elements of the matrix. We have orthonormal constraints, so it's better to, in general, express this relative orientation in terms of angle axis. So we can define the orientation error in terms of the angle axis representation. And first, let me tell you, there are also different ways of representing the orientation error in terms of angle axis. The way invented by Luch in the 1980 is this one. And so whatever I explain you is with the angle axis, you have the delta theta scalar that is a rotation, the angular rotation around the axis r hat, which is a unit vector. So you could define, we will see the orientation error just as r delta theta. But if you use this specific way of defining the orientation error, it's possible to prove that we can link easily the orientation error to the element of the relative rotation matrix that we just computed. And the relationship is this one. So it's quite simple. So you first compute the relative orientation matrix, and then from the element of the rotation matrix, you can get the 3 components x, y, and z of the orientation error. Note that the orientation error is expressed in what? In the reference frame, that in this case is the effector frame. Otherwise, as I said, we could define the orientation error in this way, just multiplying the delta theta times the axis direction. And we use the formula that we explained in lecture E02 to compute separately the axis of rotation and the scalar delta theta. And in the lab, I will use tomorrow this expression. Now, as I said, note that the orientation error is expressed in the frame E. So if we want to map in the same frame of the Jacobian in the Jacobian transpose, where the Jacobian and the Jacobian transpose are defined, which is the Ward frame, we need to compute, for example, the restoring moment. We need to map this orientation error into the Ward frame. Otherwise, you will see nothing will really work. You can try to implement yourself and avoid doing this rotation. We'll see the controller gets crazy. And this is something is not really said very clearly in the textbook, just but it's very important for the success of the controller. Okay. Is everything clear? So let's now define in another way the orientation error using, for example, the other representation that are the Euler angles. In the case of the Euler angles, things are more easy because you can define the orientation error the same way as the position error. So you take the set of Euler angles representing your desired orientation, and you subtract to that the set of Euler angles representing your actual orientation of the end effector. And to get phi d and phi e, you can extract them from the rotation matrix WRD and ERD. And you remember we had the formula with the Atan-Chu over with expression. So in this case, if we compute for example, the stiffness moment, the same way as before, the moment, resulting moment will be will be defined in a frame that is as non-orthogonal axis, because we know that Euler angles are subsequent rotations, and therefore are not part of a vector space. So we need to be very careful. But we know also that the analytic Jacobian that we define after the geometric Jacobian, it maps, remember, it maps joint velocities into end effector velocities and Euler rates, so derivatives of the Euler angles. Therefore, we can use the analytic Jacobian instead of the geometric Jacobian whenever it comes to map to torques. So this is the analytic Jacobian that Octavio explained. We take just the angular part of the analytic Jacobian, and from joint velocities, we can compute the Euler rates phi dot. And using the kinetostatic duality, we know that using the transpose of this Jacobian, we can map in the dual space of the forces or the moments, in this case, the moments defined in the Euler space into, which is not a space, sorry, m phi, into torques. So the problem of this approach is that the stiffness matrix will not be really a spring. It will be something very weird that for small orientation is a same of a Cartesian stiffness, but is using Euler angles to be defined. Then we miss the we miss the angular velocity part because we want to do a PD control law. So we are using the analytic Jacobian for the stiffness, and for the angular part, because omega is already an Euclidean vector, we still use the geometric Jacobian. If we want to use the Euler rates for the damping part, then we use in both cases the analytic Jacobian, and in this case we compute the error in the Euler rate from the desired Euler rate into the actual one, from the actual Euler rate to the desired one. And what is the problem of the shortcoming of this approach? You remember the relationship between the analytic Jacobian and geometric Jacobian was this T matrix that is nonlinear, depends on the orientation, and maps the Euler rates into angular velocities. So, and this matrix is has the problem that can become singular, especially in our convention that we choose in this work course, which is the ZYX convention. It becomes singular for a theta value of the pitch angle of pi half. So whenever the pitch is like this. So we have representation singularity. This is one shortcoming, and another shortcoming is also that we need to derive the Euler angles relative to the orientation, actual orientation from the rotation matrix, which has this remember expression with the Atan-Chu, which is quite complex. Because of course there is no closed form expression that links joint positions into Euler angles. And the third fact is that there is also singularities not only at the velocity level because of t, but also at the coordinate level between the rotation matrix and the Euler angles. So in the convention that we choose, the singularities at the velocity level are the same than at the coordinate level, and are for theta equal to pi half, plus or minus. But remember that using different other conventions, you could have different singularities in different configurations. Okay. Finally, the last way of computing the orientation error is using quaternions. Remember, the quaternions doesn't have this problem of singularities, and quaternions are for the are elements that have a scalar part and a vectorial part. And to compute the quaternion error, we first compute, as we did for the Euler angle case, compute the quaternion relative to the actual and desired orientation. So there is a way to extract have a mapping from the rotation matrix to the quaternion, and this is the expression. You have this ugly expression, which is nothing more than the trace plus 1 square root, and you can compute the quaternion, which is a 4D vector with the scalar part and vectorial part. In this way, you can have more details in this document that is referenced at the end of the lecture. So from the actual orientation and the desired orientation, we compute the two quaternions, QE and QD, and then the composition, we need to compute the quaternion error, and we do a similar way as we did for the rotation matrix. So we compose quaternions, and quaternions, they compose the same way as rotation matrix from left to right, and the formula that is used is the one for quaternion multiplication, which is represented with this symbol here. And so, for example, if you want to compose rotation 1 and 2, the same way you compute the relative quaternions, and you compose quaternion 1 and 2 to obtain the final orientation of quaternion 3. And remember, these are subsequent rotations. The formula of quaternion multiplication is the following one. Remember, in the lecture on the quaternions, we express this way, and this is the scalar part, and this is the vectorial part. So this is something that is belonging to R, and this is in R3. Okay. Then we want to compute the quaternion that represents the relative orientation of a frame D with respect to the vector frame. And according to what we explained, we have the expression of before with the rotation matrix that represents the relative orientation of D frame with respect to E frame. And we do the same for the quaternion, where we compose, remember, this is the inverse of a quaternion. So this is the inverse of a rotation matrix between from word to and effector. So the quaternion QE, which is related to WRE, it should be inverted too. And to do the inversion, in essence, we flip the vectorial part. So this is the scalar part, mu E, and the epsilon E is the vectorial part. And to compute the inverse of the quaternion, we just flip the sign of the vectorial part. Then we do a composition with the quaternion D, which is related to the orientation of the frame D. And this has this expression, and if we apply the previous formula of matrix of quaternion multiplication, we get the following expression, where we have the scalar part and the vectorial part. And in this case, the orientation error is just taking the vectorial part of this quaternion. Remember that this orientation error is still defined in a E frame, so you need to rotate into the W frame, into the word frame, before computing your control law. Okay. Then the advantage of this representation, it has no singularity, and as the other representation also requires an intermediate computation of the actual quaternion from the rotation matrix that represent the actual orientation, because there is no direct mapping from the joint variables. So in the case of the desired quaternion, just compute once, while for the actual one, you need to continuously compute according, while the effector is moving according to the actual orientation. That is changing, and is changing with the joint positions. Okay. Everything is clear. Are there any questions? So if everything is clear, then we can move to the next topic, which is the continuing the lecture of Octavio on interaction control. I just wanted to finish this one on the task-based control. And so we go back to the slide where Octavio arrived. Octavio, can you see?
Yes, we can see.
Okay. So we can move on from here. So you remember Octavio started to introduce the way you can control interaction. There are active methods and passive methods. Passive methods involve the introduction in the kinematic chain of some passive elements, and passive means springs or damper that do not produce internally any energy, but can be used like the RCC devices to accommodate the interaction forces that can emerge if you have some interaction with the environment, and your geometric trajectory is, for example, entering in the environment. And this is a way to limit the interaction force using a compliant passive element at the end effector. On the other hand, we have active methods that which we design a control law such that the robot can react in a specified way to the contact forces that are applied by the environment on the end effector. And we can measure these forces via a force sensor, a 6-axis. You remember a force sensor that is made with strain gauges. And the most naive way to compute the control interaction, is direct force control, is just trying to minimize the error, the force error. So we have the measure of the force with the force sensor here. And we apply this control law, and we see that we end up with a dynamics of the error in force that is converging to zero. The drawback of this approach that tries to control directly the force is that it can lead to instability very easily. So we can have for example, there is something in the middle that we are going to explain in this lecture, which is impedance control. So in the middle to what? Till now, we explained, for example, position control, which is a controller that tries to control position no matter what force is applied in the effector. And there's this advantage to achieve very high accuracy. It's very stiff. And the drawback is that you can have, if you try to achieve your goal at any cost, you can have high interaction forces whenever you are in contact with the environment, and you can have a problem of reaching saturation of actuator, for example, or breakdown of the mechanical parts. You can damage, for example, the actuators, so you can break the gearbox. While in the approach where we directly control the force, we control the force no matter what position is achieved. And as I said, the problem are instabilities that can arise if you increase the gains in the force error, for example. But there's something in the middle that, is impedance. Here, that is in the robotics community, it's very common to implement whenever it comes to interaction, and is impedance control. And what impedance control does is to make the robot match a desired interaction model that relates displacement to contact forces. So rather than directly regulate the contact forces, it generates a motion that satisfies a dynamic relationship, for example, the one of a spring. So more generic, a spring can be extended to a mechanical impedance, because a mechanical impedance has also a possibility to emulate the terms about damping, so a velocity dependent term, and about inertia, so an acceleration dependent term. So in essence, it makes the manipulator that is interaction with the environment behave like a virtual spring mass damper system. Okay. So what is mechanical impedance and what is impedance control? So in impedance control, to design our control law, we do something very similar to what we did in the task space, in the Cartesian space inverse dynamics. We first step do a feedback linearization that allows us to define allows us to linearize the system, and then assign the desired behavior that we want for our end effector that is defined by this reference model that is called the impedance. We will see some variants and simplification that simplify this formulation that will ease and simplify the implementation of this controller. So what is a mechanical impedance? Is a relationship between forces and velocities or position in a certain point for a certain mechanical system. While the admittance, we will see also the admittance control is just the reciprocal of the impedance. So in how this impedance looks like as the form of virtual mechanical system with a mass matrix MD, which can, for example, we can set to be diagonal, and a damping matrix DD desired, that is we can choose as we want, and the same also for the stiffness matrix KD. Sorry, this. And usually impedance control is implemented in the Cartesian space. There is not much a sense to implement it in the joint space, because our interaction forces are usually happening at the end effector level. The choice of this impedance parameter, MD, DD, and KXD, are usually coming out from a trade-off between how accurate we want to track our reference position and how high are the contact forces that we allow in the system. And this is the expression wherever we have the impedance defined at the joint level. And as I said, this is not really used in practice. Okay. So intuitively, the impedance gives us an idea of how a point in a system will move whenever you apply a force to it. In this case, for example, if we consider the end effector point and we want to define the impedance with respect to some reference position that we want to track, we can make such that we emulate a virtual spring between the end effector position and this reference state that behaves. We can emulate some virtual spring that tries to make our end effector go to the reference point. And whenever a force is applied externally, this point will move away from the reference point in a impedance way. So following the desired impedance that we define. So in essence, our robot becomes a second order system that is stable if you set positive definite stiffness and damping matrix, and that is attracted by our reference position, for example. And whenever you remove the contact force, the external force from the environment, the end effector will go back to the reference point. So the advantage is that we don't need an environment model that describes how the reaction force are generated by the environment as a consequence of a deformation. And also there is no way, in essence, to regulate the contact forces directly because differently from before in the direct force control case, we are missing a force error loop at the end effector. And therefore we cannot control forces, but for example, defining the stiffness, trying to keep them small, and the contact forces will be emerging from the motion we do. So according to the stiffness we set, given a certain motion from the reference point, this will be strictly correlated to the contact forces that generate that motion. I don't want to say here that, so think about the fact that we are talking about the end effector. So a force error loop is, we are not closing the loop at the end effector, but in general, the implementation of impedance control, they always use a torque loop. Remember, we have our, all our control law that are setting a desired torque for the robot. So we need to think that also the impedance implementation will send the desired torque to a low-level torque controller that runs at the joint level. So there is a closing the loop on the torque, but at the joint level. Typically, we define a reference trajectory for the impedance controller that can be constant in time, in space, or time varying, moving around. And in this case, the impedance will have the following form. Where we have the acceleration of the end effector minus the desired acceleration of our trajectory plus so this is the desired inertia that we want in our impedance, and this is called apparent inertia, which, because the inertia that a user, for example, touching the end effector will feel at the end effector. The end effector will hide whatever the inertia that the manipulator has behind. It could be a robot of 2 tons or very, very heavy and very big, but it can be at the touch felt like a 1 kilogram mass if we want with this approach, because this approach allows us to shape the inertia. Then we have a damping part, which is desired damping. This should be positive definite. Of course, also the inertia should be positive definite. Finally, you have the desired stiffness. This is desired. And again, we have the error between the actual and the desired trajectory, and this is the external force coming from the environment. Okay, so this is the behavior we want to impose at our end effector. And these matrices are, of course, have the dimension of the end effector space. So case we will see now. Let's consider just the position on impedance, a linear impedance. So the Cartesian case, and then in the end of the lecture, we see the how it extends to the angular case. So let's consider for now m equal to 3.
Excuse me.
Yes.
Why don't we write P desired minus P like we did in the other lectures for the error?
Yeah, because this is not a control law. This is a mechanical system. This is the behavior, desired behavior that we want, and needs to be defined this way because otherwise you would have a negative damping. So this is a spring mass system. So if I have this to 0, remember, I have the equation that we explained in the control law, in the control lecture, that represent a second order spring mass system, right? Here we are just defining the discrepancy with respect to some reference values. But it should be this way.
Okay, clear.
Otherwise, it becomes unstable if you use the other one, because this is an external force is making my point, my mass, my virtual mass, accelerate in the same direction. Otherwise, if there was a minus here, you apply a force, and the mass will accelerate in the other direction. It is not physical. It's not a mass, no? And the same for the stiffness. If you compress a stiffness, you can have a negative spring, but I mean, you can see from the acceleration here. And so if we have our real dynamics, that is the one we started to introduce in the constraint dynamics class. We have the free motion part, plus we have the external contact forces that are entering in the equation through the Jacobian transpose. So differently from the constraint dynamic case, where we were considering forces and effector that are generated by the attempt to violate the constraints. In this case, we consider just these forces are coming from the measure of an external force sensor. And if we now, sorry, this is the geometric Jacobian. And if we do the second derivative of the Fourier kinematics, remember we can link the joint acceleration to the and the effector acceleration minus J dot Q dot. Okay. And this is the we use the inverse of a Jacobian just to simplify, to start from the simple case of a non-redundant manipulator, but you know you can use the pseudo-inverse, and we can plug this expression in the previous one, and in essence achieve what we did in the case of task space inverse dynamics, to get the torque commands that are performing feedback linearization in the Cartesian space. So I get whatever was before. I think I put tau, let's put u. So I put m q dot dot, I replace the expression I just found, which is j minus 1 p dot dot minus j dot q dot. And then I sum up. I want to cancel the Coriolis and centrifugal terms, and I want to cancel the contact forces. Note that we have a minus here because we are on the same side. The torques, you are on the same side of the contact forces. So if you want to cancel them, we need to do the sign change. And if we, then we take the previous behavior that we defined in the impedance model, and we express the acceleration, desired acceleration that we want at the end effector. And this acceleration is the acceleration that, in essence, realize the impedance that we want. So given an external force, contact force, this is the acceleration that will make our end effector behave as our desired impedance, which is composed by the desired inertia md, the desired stiffness kxd, and the desired damping dxd. So in essence, we is equal to pw dot d mxd minus 1, and we have dxd p dot b minus p. And the student that asked the question, you will see now that we recover back in the control in the controller the way of expressing the error in the same usual way we always did previously. Sorry, and this is plus fx. Okay, yes. So now we can see that with this law, we linearize the system, inverting the dynamics to eliminate whatever is not convenient, and express our system as a double integrator in terms of what? In terms of a new signal that we, in the task-based inverse dynamics lecture, we call V. And then we want to apply our desired behavior of the acceleration to the acceleration of this new system, which is simply a unitary mass set of unitary masses of let's say of double integrators, such that these masses behave like an impedance, our impedance, desired impedance. So if we replace that and we substitute, we obtain the final control law, which is mj minus 1, use braces here, q dot plus mxd minus 1 kx d ax, which is this, plus dx d ax dot plus h, remember this term here, minus j transpose fx. Plus we have this other term that I separate. So it will be mj minus 1 mxt minus 1 effects, so I can collect effects in both cases from the two inputs. I see that I have effects here and effects here. So I can collect them, and I have j minus 1 mxd minus 1 minus j transpose fx. So we have effects appearing both in the feedback linearization and in the choice we made for the acceleration to map the impedance, which is the equation 3. And in essence, the problem is that this effects, we need to measure it with a force sensor. So everything else that is in here is related to proprioceptive sensors, encoders, and so on. But this requires a six-axis force sensor. And it is difficult in general to achieve a perfect cancellation, okay, of this with the effects that we measure with the real effects, that because you have sensors, biases in the error bias and offsets in the six-axis force sensor. So we'll see that we can define a simplification of this that gets rid of this term. But for now, this is the most general expression that realizes, this is the control law that realizes a desired impedance at the end effector with the following parameters: dx, kx, and mx. Okay. And what can be useful, for example, the inertia shaping, the fact that we can set mx. So in here, this is very similar to operational space inverse dynamics, but the difference is exactly that in the operational space inverse dynamics, we don't have fx in the expression, and we are not able to shape the inertia. The inertia is always the operational space inertia, which is the joint space inertia reflected at the end effector. While here we can shape the inertia, and we can, in essence, mask the true inertia of the manipulator, and as I said, impose a desired one at the end effector. So we are not really changing the manipulator inertia, but we change the apparent inertia, which is the inertia that is felt at the end effector. So for example, if you have a configuration dependent inertia that depending on the joint configuration is continuously changing, you can make such that this inertia is always constant. For example, this is useful in case of you want to do a rehabilitation robot and you want that the patient always feel the same inertia at the contact and is interacting with the robot to do some rehabilitation. While instead, if we get rid of this feature and we say, okay, we don't care, and we choose the desired inertia the same as the real inertia at the end effector, which is lambda. You remember the expression. This is the one for redundant robot. That works also for redundant robot, and you see that you have a dependency on the joint configuration. If we do so, magically, and you replace in the previous expression, the need of an external contact force sensor is disappearing, and the fx disappears from the equation. And in essence, you get whatever is a PD in the Cartesian space, where you compensate also for Coriolis effect, and you have a feed-forward term from the acceleration that you map at the joint level. So this is a PD, an hybrid thing with some Cartesian space PD plus some compensation of correlation and gravity, and a feed-forward term, which is the vector acceleration mapped at the joint level. This is q dot dot, and this is this is q dot dot, and you multiply by inertia. So remember the feed-forward term that we introduced in the PD control, joint control class. Everything is expressed in joint coordinates, so this is very desirable and simple, but we have non-constant apparent inertia. And also this inertia is nonlinear, because now the impedance felt at the end effector is no longer joint independent, but is dependent on the joint configuration. So it's this expression. Sorry, these are flipped. Okay. Now we can further simplify this control law. We see that whenever there is no external force, we will have no displacement from the desired position. And if we set the desired position to be constant, so zero desired velocity and acceleration and constant position, the control law simplifies to Cartesian PD plus gravity compensation. So the control law simplifies to this one. Okay, because we are considering constant trajectory reference. For small displacement, assuming that also gravity is compensated, we can say the following. This simplifies even further. First, observe that for small displacement, we have that the displacement PD minus P could be expressed with the Jacobian. And the control laws becomes, if we don't consider gravity for now, J transpose Kx T J QDs minus Q. And this is what we call the compliance control. And what is interesting to observe is that this is the stiffness at the joint level. So there is, if we set a desired stiffness at the task level, at the effector, at the task level, we see that this maps, because of the Jacobians, into a variable stiffness at the joint level. Why it is a stiffness defined at the joint level? Because it relates increments into joint variables into torques. Okay, you could see this the same way doing the following trick. You have a delta Q, you know that through Jacobian, for small displacement, you can take a delta P. Then delta P is related to Cartesian forces through the stiffness matrix. And then the Cartesian forces through the J transpose, you can compute the torques. So in essence, doing this thing is just doing J, Kx, J transpose, which is applying first J, then Kx, and then J transpose, and this is the same as doing the Kq, which is the stiffness at the joint level. Yeah, this is just a detail. If you want to, your boss arrives and wants you to implement a stiffness at the Cartesian level, you have only a joint space controller. You don't want to waste time. You take your Jacobian, you take your desired stiffness, you do this computation, and you control you implement impedance controller at the joint level. That I didn't, in this case, is the only case whenever is useful to implement impedance control at the joint level, and you are done. In essence, you apply your torque like this way, and you're sure that at the end effector you have something that for small displacement and for very slow motions is behaving like a Cartesian constant stiffness. Then another cool thing about impedance control that dictated the success of this approach is that because impedances are linear, like linear mechanical systems, you can do superimposition of effect. You have that holds the superimposition, the principle of superimposition of effects, and you have that you can superimpose the effect of two impedances, and therefore you can have multiple tasks achieved at the same time. Of course, the output behavior will be a compromise between the task if the case they are conflicting, but you can define a task and tracking a point with a certain impedance and tracking another point with another impedance, and you can achieve something in the middle. Think about a robot, a legged robot that needs to control the center of mass to stay inside the polygon. So you define impedance for that one. And there's also an arm on top of that needs to reach a target. And in that case, you have another impedance. And if you set the target too far away and the arm will extend, and at some point there will be a conflict because the robot will try to track the target with the arm, but will move the center of mass out of the polygon. So these two tasks will have to find a compromise. Then the very important topic that is nobody really talks about is how do you select impedance parameters. People implement impedance control, and now they need to set some values for this stiffness and damping matrix and inertia. And this is a way to, according to my experience, also to Professor De Luca insights, way to tune these parameters. So first you need to think about what are the admissible contact forces that you accept at the end effector, and also the desired transient that you want. So we want, for example, to avoid large impact forces when entering contact and when we keep the contact. And these large forces can be due to the fact that we have we are defining our reference trajectory, for example, inside the environment. We will see that this can happen, for example, if we don't know that there is an impact in that point. And so you, in essence, select the stiffness matrix according to how much force you expect in a certain for a certain deflection. And if you increase the stiffness, you will have a higher force for the same deflection. And the thumb rule is, in general, to adapt the impedance to the dynamic characteristic of the environment. So if you have a compliant environment, you want to be stiff, while in the case of environment that is stiff, you want to be compliant to reduce the contact forces. The extreme case is whenever the robot is in free motion, in which the environment is infinitely compliant, and therefore you achieve the highest stiffness because you want the highest positioning accuracy. In terms of the desired motion that we want to set in our control law, PD, the desired position, for example, of the end effector, we try to plan inside the environment. This way, we are sure that we will keep the contact active, and the impedance controller we achieve according to the stiffness we set a certain contact force. And this is important, for example, if you want to do a cleaning task and you want to follow a surface and you want to be able to clean the surface, you need to apply certain force. Okay. Then the inertia, how to select the inertia. We can select inertia according to how light we want to feel the robot at the end effector. Especially if we know the direction where we expect the contact, we try to set a higher impedance to reduce acceleration and a lower stiffness to reduce the impact forces. While in direction where we expect to have no contact and we have only a free motion, we want to have a fast acceleration. So we set a lower value for the impedance of the inertia for that direction, and to achieve a good tracking, we can set a high value for the stiffness for that direction. And to finalize, the damping term is the last one that you select at the end of the process. And you select that to guarantee that there is no overshoot, because remember, we have a second order system. So to avoid having overshoot, you selected damping to have a critically damped response. And whenever you are given the value of a stiffness matrix and the inertia matrix, doing the square root of 2 square root of kx mx, you can get the value of dx to achieve the critically damped behavior. So as an example for the desired pose or desired defector position, sorry, in this case, no, this is a pose. So we have also the orientation. We'll see later how to define the impedance at the orientation. Let's say this pose, so this position and orientation is constant in time, and we have the human interacting with the end effector. And in this case, the user is carrying around the end effector, and when the human will move the end effector, this will generate an error with respect to the desired pose XD. And in response to this, the robot will generate a force according to the impedance model. If you make the robot very stiff in one direction, then the human will feel the need of a higher force to achieve the same amount of displacement. If in another direction you set a lower stiffness, then for the human will be easier to displace the end effector, and you will use less force to do that. And if you use a high apparent inertia, the human will feel a heavy robot, the end effector, to be moved, while with the low apparent inertia, the feeling will be like to move a very light object. And this is very important for collaborative tasks. And the important thing is that we can implement this approach of impedance not only at the end effector, but at any contact point. And in another example of reference trajectory, reference pose, that is time varying, for example, is whenever the robot needs to write on a surface. In that case, he needs to keep the contact of the pen with the surface, and we set the reference trajectory slightly inside the surface. This is an example of sanding and polishing of a piece after the machining. You can use impedance control for that. And this is the example of the IQ leg where we implemented stiffness, virtual stiffness and damper between the foot and the hip, and we can set the important thing of active methods is that we can change the stiffness via software in real time, and we can achieve different stiffness profiles. We can make it soft and we can make it stiff in a millisecond in essence. And this is really the advantage of active methods. Of course, if your inner loop, torque loop is not fast enough, you might have some issues of instability in the very initial moment of the impact. That's why we implemented a very high bandwidth torque loop at the joint level. In case of the rotational impedance, is the same as the linear impedance. So we just use consider these springs no longer as we explained before, no longer linear but torsional. And again, usually people do this using Euler angles, defining desired orientation, PD and actual orientation, finding the error, and implementing the desired impedance, desired angular impedance, sorry, this way. So here we get acceleration and velocity, and delta phi dot plus delta phi. And here, remember, we need to use the do the Jacobian transpose. Sorry, instead of using the Jacobian transpose, we need to map the. We have the moment, let's say, that is defined in the Cartesian space, and we need to use the matrix T. But remember, the matrix T is for the velocity level to map Euler rates into angular velocity. And here you want to use the transpose of that to map moments into moments that are at the level of Euler angles. So this is an impedance at the level of Euler angles. And as usual, this T matrix has problem of representation singularities. So in essence, instead of using the equation free, remember to define the impedance behavior in the linear case, you use this equation to define the desired behavior, the torsional case, and you use the previous law, and that's it. And if you look at this example, you can have here the translational compliance and a very low and a very high torsional compliance. So the user is trying to tilt, but is not able to rotate the end effector. And in this case, the other way around, is set a very low rotational compliance and then a very high translational one. So it's not able to move it linearly translating, but it's able to. Cool. Okay. This one doesn't disappear, and I understand why. There is no eraser. Bad. So there are some issues with PowerPoint. Sorry about that. It's crashed. Okay, that's why. Yeah, sorry about this, because if I start from the slide, it doesn't forward properly the screen on the room here. Sorry about that. Can you see everything now?
Yes, we can see.
Okay. In essence, I will start to talk meanwhile. Yeah, there is another way of looking things is the ambiguous control, which is the opposite, the dual way to impedance control. And so far we consider in impedance control as input commands to our robot torques that should be applied by the motors, for example, through current or through a low level torque loop. And however, in some cases, and this was common, especially in the past, the robots, industrial robots, provided only an interface, a position tracking controller, and so you could only set some velocity reference or some position reference. And in these cases, you don't have access to the low-level controller, and you can command only position or velocity. So what can you do whenever you are in presence of interaction forces? In this case, researcher invented the admittance control that relates contact forces to position to reference position commands. And these approaches always need a force sensor to measure the contact force. And the idea of admittance control is that whenever there is an interaction force, the controller modifies the set point of the position control in such a way to, as in the case of impedance control, satisfy this dynamic relationship of impedance. Let's do here a very simple example on compliance. So consider only the stiffness matrix. And we can do this implementation both at the joint level or in the Cartesian level. And we can consider a displacement at the end effector from the measured contact forces. So we measure the contact forces, we divide by the stiffness, and we get the displacement at the end effector from the reference position that we should have, such that our end effector emulates the behavior of a spring, a virtual spring of stiffness Kx. And this is called compliance. It's just the reciprocal of the stiffness. And this increment, again, we could map, if it is the increment is small at the joint level using the Jacobian . Okay. And of course, in case of redundant robot, we should use the pseudo-inverse. This matrix, compliance matrix, should be positive definite. And that's it. We have implemented our admittance control law. So, no, we didn't finish to implement. We compute the increment. And in the joint space, you can do the same. It's even simpler. You just have the stiffness matrix implemented at the joint level, and what you need to do, you need to from your sensor measurement, you map the external force at the joint level, and then you multiply by the KQ minus 1, you get the increment. And also this should be positive definite. Now, what we do with this KQ, we modify, in essence, the reference position, QD. So the next step, we take our reference position, we add the KQ, the delta Q that we computed. And this reference position is given to the position controller. Note that you can implement more complex admittances. In this case, we are using the Laplace transform because it's a nonlinear system. Is a linear system, and we can, in addition to the compliance, we can have also as is in the case of the impedance controller, we can have also the desired damping and the inertia, the apparent inertia. And an important comment is that. Actually, admittance and impedance controller have a duality also in terms of where to use them. So admittance controller are good in presence of low impedance environment and are very good to render high impedances. So very small deviation you saw. while for high deviation, you have the problem that the Jacobian is not representing anymore the approximating the small displacement, and the big displacement means that you need to move a lot the end effector with the position controller to emulate, to give away to the force. So if you have to emulate a small compliance, you have a force, and you see that the end effector needs to move a lot to emulate a soft spring. But if you have a position controller that is not fast, you are limited. You cannot do that for very soft compliance. While the impedance controller is the other way around. You're able to easily render low impedances, especially when you are in contact with stiff environment, but you cannot really increase too much the stiffness, because then you get the problem of instabilities that you can have also here. The peculiarity is the inner loop that discriminates them. In the case of emitters, you have a position or velocity control, while in the case of impedance, you have a torque control as an inner loop. Okay. Do you have any question? Finally, the very last topic of this course is about visual servoing, which is the visual interaction is just another type of interaction with the environment. Is an interaction that has no contact. And in general, we saw in the sensor class, exteroceptive sensor class, the usage of sensor for robotics is to gather the information from the environment without contact. And usually whenever the scene around the robot is acquired and the robot position and orientation can be planned according to this visual feedback to drive the end effector to track, for example, an identified object. And it's not only that, but the concept of visual servoing is that you can use this visual measurement to close the loop directly on this image feature that you want to track. And you can control so the position and the orientation of the end effector, closing the loop on the visual feedback. This means that if you have a visual feedback and you are doing this, you need to have a real-time feedback signal, because if you have delays and you're closing the loop, as you saw in the control lecture, you can have instabilities. And this is an example of visual feedback wherever you have a depth map or the height map of the environment. And some examples of visual servoing, you can have, for example, the robot is trying to catch a ball that is flying. Or a more useful example in industry is whenever you need to pick and place object from a, picking object from a box. This is very important. Think about Amazon warehouse. At the moment, the pick of the object is not really automatized yet, but will increase a lot the productivity of the warehouse if the robot is able to see the object and grasp it from a box. And the last one is the, for example, following the contour of a corner in a contour of a shape in a deburring task, or whenever you need to follow the edge. The first decision to be made whenever you set up your vision-based control system is where to locate the camera. And the camera can be located either outside the robot in the workspace in a fixed location, and this is the case of the eye-to-hand approach. And in this case, the camera can observe the manipulator and any object to be manipulated at the same time. While in the other case, you attach the camera to the end effector and the camera will move with the end effector. And this is the eye-in-hand configuration. And you attach the camera in essence to the wrist. And the advantage of the eye-to-hand is that the field of view does not change. You have a fixed geometric relationship between the camera and the workspace. But the problem is that as the manipulator moves, it could occlude the field of view of the camera. While in the eye-in-hand configuration, you have never occlusion, but the geometric relationship between the camera and the workspace changes as the manipulator moves, because the kinematics changes. And also the field of view can change a lot, even for a very small movement. And finally, there are two control architectures. As I said, the position-based one, look and move, in essence, use the vision system just to provide set points for the estimate of the position of the camera, for example, and giving a certain set point, you create a task Cartesian error, and you can use our joint controller to track, to close the loop and track the position of the end effector. And in this case, the sampling rate of the visual signal is not a problem, even if it is low, and because we close the loop at the joint level. While the other approach is what I drafted you before, is the image-based one, and it is visual servoing. And in this case, we close the loop directly on the image data, and we create, for example, an error function defined in terms of quantities in image plane. So we have some feature, we want to track this feature, we have an error in the image plane. We, from the kinematics, we map this error into joint commands. And in this case, of course, the rate the visual information is coming is crucial, because if you have delays, you can have instabilities because you're closing the loop at the image level. So here you have some examples of this. This is the look and move, the position one, where you move the end effector in order to match the shape and align with the shape you see. And in the bottom one, you see this, you see these blue dots that should match the red dots on the box. So the robot is moving, trying to reduce the error in the image between the blue dots and the red dots. And this is an example of a visual servoing one. Okay. Do you have any question about this? Okay, if you don't have any question, we do a break now of 15 minutes break. And the theory of the course is finished. We miss the labs, the joint space control lab and the task-based control lab that we'll do today and tomorrow. And these labs are in the LocoSim framework that you should have the link And I ask you in this break to pull the latest commit and do git submodule update to have the latest version of the software. And you can find the PDF of the lab inside the LocoSim folder in the lab descriptions, but I will also put them in the PDF folder as usual. Okay, so let's come back at 35.